So this is we are going to calculate the electric field produced by infinitely long thin wire. We've already done this with with Coulomb's law in chapter 21. We'll look at how we can do this with Gauss's law, right? Okay, so the first thing that we look at is when you have a wire with charges uniformly distributed on it, an infinite wire, what kind of symmetry is this? Is this spherical symmetry, or is this cylindrical symmetry, or is this planar symmetry?
Cylindrical.
Cylindrical symmetry, because if this is my infinite wire, this pencil is my infinite wire with charges on it, if I turn the pencil, you cannot tell that it's been turned, right? So that's a cylindrical symmetry, but there's only one axis about which I can turn the pencil. If I turn it about a different axis, like if I rotate it like this, you can immediately tell that it's been rotated. So this is cylindrical symmetry, which means that the electric field lines will be cylindrically symmetric. Now, suppose you have the wire coming out of the page like this. What kind of field lines would be cylindrically symmetric? There are only two possibilities. The field lines could be radially outwards or radially inwards. This is consistent with cylindrical symmetry because if I turn the wire, the field lines will look the same, right? That's one possibility. There is, just for completeness, there is another possibility of field lines which are consistent with cylindrical symmetry, and I'll just mention it over here. So this is our wire coming out of the page. Suppose the field lines, okay, I'll just write over here. So suppose this is our wire coming out of the page. Suppose the field lines were concentric circles like this. This would also be consistent with cylindrical symmetry, because if I were to rotate the whole figure a little bit, you will not be able to tell that anything has changed. That makes sense? So the two possibilities which are consistent with cylindrical symmetry are field lines which are radially outwards or inwards, or field lines which are concentric circles, right? Clearly, this one doesn't make any sense, because we know that field lines always come out of positive charges, right? Or go into negative charges. So this first one doesn't make any sense, and we are not going to consider it anymore. So it seems that the only possibility is that the field lines are radially inward or radially outwards. If the charges on the wire are positive, then the field lines will be radially outwards. That makes sense? Okay, so what kind of Gaussian surface should be considered? So the electric field lines are all coming out radially outwards. So it makes sense that we should take a cylindrical Gaussian surface, because there is cylindrical symmetry in the problem. So our Gaussian surface is this imaginary cylinder that's drawn over a part of the wire. The length of the cylinder is little l. That makes sense? Okay, so what we have to do is calculate, and our Gaussian surface obviously passes through the point where we want to find the electric field. So it has a radius r. So let's say we want to find the electric field somewhere over here. And so we are drawing our Gaussian surface, which is a cylinder, through this point. All right. Now, we have to evaluate Gauss's law over this cylindrical surface, right? I'll draw a few field lines for you. So the field lines are all radially outwards. I've just drawn a few of the field lines. Okay, now, what is the flux? So the Gauss's law says that the flux of the electric field over the Gaussian surface is equal to Q enclosed divided by epsilon 0, right? What is the flux over surface number 1, this flat surface? Let's call this one a surface number 2, the other flat surface. So what is the flux over this flat surface, surface number 1? The answer is 0. That makes sense, because none of the field lines are penetrating that flat surface, right? So flux over surface number 1 is 0. What is the flux over surface number 2, the other flat surface? The other flat surface, what's that going to be?
Also 0.
Also 0, very good. So there is no flux over the two flat surfaces, but there is going to be a flux over the curved surface of the cylinder, right? Now, this argument is going to be very similar to spherical symmetry. So let's consider a tiny patch of area, which is indicated in this purple thing, dA. And just imagine that dA is very small. So dA is going to be r hat times dA. R hat is the radially outwards unit vector. And what about the electric field? The electric field will have cylindrical symmetry, which means that its magnitude only depends on r, and it will be radially outward, right? So you can see how similar this is to the spherical symmetry case. So we have the same dA and the same E. And so if you calculate the flux over the curved surface, that is going to be surface integral E dot dA. And we can skip all the steps in between. And so it's just going to be E of R multiplied by the area of the curved surface. Now, what is the area of the curved surface of a cylinder?
2 pi r times the length.
2 pi r times L, right? 2 pi r is the circumference and L is the length. So it's going to be 2 pi r L, exactly. And we are done with the left side of Gauss's law, right? So I'll just write everything over here. So this was our wire, this was our cylinder, this was surface 1, this was surface 2, and this is surface 3, the curved surface. So we already saw that phi 1 is 0, and that's also, and phi 2 is also equal to 0. Phi 3 we calculated, so it's surface integral E dot dA, but this is just going to be E of R multiplied by 2 pi RL. That makes sense? And so that is the total flux if you add these three up. And that is equal to, so the total flux, which is 2 pi RL, or the total flux over our Gaussian surface, is going to be equal to the Q enclosed divided by epsilon 0. Now we are told that the charge density on this line is lambda, right? And the length of the cylinder is L. So how much charge is enclosed by the cylinder? How much charge is inside our cylindrical Gaussian surface?
Lambda L.
Lambda times L. Is everybody clear about that? So the charge that's intercepted by our cylinder, the charge inside our cylinder, is simply lambda times L. So lambda times L divided by epsilon 0, right? And we just saw that the total flux is just the flux over the curved surface. So that's just going to be E of R 2 pi RL, right? And we are done. We can solve for E of R from here. And it's just lambda, L's cancel out, over 2 pi epsilon 0 R. And you can see how easy this was. If you recall how we did this in chapter 21, we first calculated the electric field due to a finite wire, which was pretty tedious. And then we took the limit as the length of the wire goes to infinity, and we got this result. Whereas with Gauss's law, it's just literally the one line of algebra and you get the answer. That makes sense? All right, so this is the electric field due to an infinite wire where the charge density is lambda. Okay, we can do one more case. And I have a similar problem, which is very similar to the sphere with non-uniform charge distribution. So I've used this one on exams too. So make sure you do this one on your own for practice. The last case that we are going to look at is an electric field that's caused by a thin, flat, infinite sheet with uniform positive density, positive charge density sigma. So this is just imagine that this is an infinitely large sheet on which you've got charge that's uniformly distributed. And we want to find the electric field at some point, maybe over here, a little bit above the sheet or a little bit away from the sheet. Okay. So how do we find the electric field over there? First thing that we notice is that this is planar symmetry. Planar symmetry means that if the sheet is shifted a little bit, if this is an infinite sheet and this is not symmetric at all, it has to be perfectly white. I don't think I have a perfectly white sheet anyway. So if the sheet is shifted a little bit, you will not be able to tell that it's been shifted, right? That's the definition of planar symmetry. So what could the electric field lines look like for planar symmetry? Clearly, the field lines have to be either coming out of the sheet this way or that way, actually coming out of the sheet both ways. So on the left side, they'll be coming out one way, and on the right side, they'll be coming out the other way, right? And so the electric field lines will be perpendicular to the sheet and coming out of the sheet on both sides. That makes sense? And so that's the only configuration of field lines such that which is consistent with planar symmetry, right? Okay, so we know that the field lines are perpendicular to the sheet. So what kind of Gaussian surface do we choose? We choose another cylinder or any other regular shape, cylinder or a rectangular box will be fine. So we choose this particular Gaussian surface which straddles the sheet. So half of it is on one side and the other half is on the other side, right? So then we want to apply Gauss's law to this particular Gaussian surface. So the total flux is equal to the charge enclosed divided by epsilon 0. And the charge density on this sheet is sigma. That's given in the problem. All right, so let's calculate the total flux. So I'll just get rid of some of the clutter over here. So again, we have three surfaces. 1, 2 is this one, and 3 is the curved surface. All right, now, is there any flux over the curved surface if the electric field lines are all perpendicular to the sheet? There is no flux over the curved surface, right? All right, so that means phi of 3 is 0. What is phi of 1? Now, the magnitude of the electric field is going to be constant over the face 1, right? In order to be consistent with planar symmetry. So the magnitude of the electric field will be the same everywhere over face 1, and face 1 is flat, right? So surprisingly, we can use our simple formula to calculate the flux. I mean, pleasantly, surprisingly, we can use our simple formula to calculate the flux. And so that is just going to be, can somebody tell me what that's going to be if this area is A and the unknown electric field is E? So what's that going to be?
Times A.
E times A, exactly. EA cosine 0. That makes sense? EA cosine 0, because the area is pointed outwards, so is the electric field, so they make a 0-degree angle. EA. And what about the flux through face number 2, the other one? What's that going to be?
Negative EA.
Let's be a bit careful with that. Face number 2, what is the direction of the normal to face number 2? It's also going to be outwards. That makes sense? So the direction of the normal is going to be the same as the direction of the electric field. Is everybody clear about that? Let me just draw another diagram here just to make that really clear. So here is our sheet. We chose a Gaussian surface which looks like this cylinder, and this part is underneath the surface. So this was our Gauss. The dashed part is underneath the surface. This was our Gaussian surface. So the field lines are going this way and this way. That makes sense? The normal to the surface is this way over here and this way over here, right? So the electric field on the upper face, this was our face 1, and this is our face 2. Electric field on the upper face was E multiplied by A, right? What's it going to be on the lower face? It's going to be the same E, because we're assuming that the cylinder is at the same distance from the surface. So it's going to have the same magnitude multiplied by A. Do you agree with that? Because on the bottom face also, the electric field and the area have the same direction. So the dot product will be E times A. And there is no flux over the curved surface, right? So the total flux will be 0. EA plus 0 for the curved surface plus EA again for face number 2. This is for 1, this is for 2, and this is for 3. That makes sense? So the total flux is going to be 2 times EA, right? And so we figured out the total flux. We can plug it into Gauss's law. Gauss's law says that the total flux over our Gaussian surface is equal to the charge enclosed divided by epsilon 0. If the charge is sigma, charge density is sigma, and the area of the face is A, then what is the charge enclosed in our Gaussian surface? How much charge is intercepted by this imaginary cylinder? Yeah, so how much charge is enclosed?
Sigma times A.
Yes, sigma times A, very good. So the total flux was 2EA. Charge enclosed is sigma times A divided by epsilon 0. And so we have, amazingly, we have figured out the electric field due to an infinite sheet of charge with one line of algebra. It's just sigma over 2 epsilon 0. And this is exactly the result that we got with a lot of work in chapter 21.